All right, good morning, everyone. My name is Dustin, and I'm here to talk about how we leverage advanced analytics and AI in telecom infrastructure planning, strategy, and design. Go quickly over the agenda. I'll give an introduction about me and my company. We'll go through a fun little adventure on how we start and finish a project in ArcGIS Pro. We'll go through how we use AI to locate utility poles to help offset costs in design. We'll go through how we detect houses with AI to help our costing models for our client. And we'll go into how we train the model, how we use those in our design, and then some closing stuff at the end. So my name is Dustin Lilly. I'm a senior technician and also the GIS automation team lead at Olson. I've been in telecom and GIS for about 6.5 years. I've also coded and automated stuff for about 4. Olson was founded in 1956 on the very mindset that drives us today. Basically, we're here to help improve communities and leave them better than when we found them. We are an engineering firm. We do all sorts of things from telecom, traffic, roadways, civil data centers, waterways, airports, you name it, we probably have a hand in it. All right, so the technical overview, there's a lot going on that slide. We'll go through some of the slides a little later. But essentially on the right is how we've built our AI, and on the left is how we integrate that inside of Esri's ArcGIS Pro. So the first thing is when building the AI, we set up a client. This is how we interact with the AI. It helps mediate between ArcGIS Pro and the Bing imagery that we use to detect objects. It is shown as a command prompt, so we can direct it where we want to go, when we want it to run, and get useful information there. The other side is the server. This is how we will view the results as they're happening in real time. This is all done local on our machine, so we don't have any other softwares that run. We can pull this up in a web browser, and I'll show a couple videos later of it running in real time as it's detecting things. So the first thing is how we built and trained the model. This is just a whole lot of text, and is to show that we built all of the scripts and have how it connects in-house. So we have more customization on what we want it to do, how we want it to look. We specifically coded it to work inside of ArcGIS Pro. So it's pulled in as a geoprocessing tool. You can see that we have different parameters like you'd see in a normal geoprocessing tool. We can control what layer is being used, the size of the images, and so on. This is what the backend looks like. This is a database file. As you can see, it has a similar structure to an Excel or a CSV or an attribute table. We have the object ID. We also have field names such as the class name, the class value, and the confidence level. For this example, the class name, we have utility poles as well as their shadows, and we'll go into why we're also detecting the shadows in a little bit. And we also have a confidence level that helps us gauge how accurate the AI thinks it's what it's seeing based on a percentage. So if you see 0.31, that's a 31% confidence level. On the bottom, we have the folder structure on how we have everything set up before we train the model. We have to have all of the pre-trained images, their labels, their annotations, and all of that work goes up front before we can train it so the AI knows what it's looking at. All right, here is an example of the web server we have set up. We have different colors for what we're seeing. We also have the database or the attribute table down below. So if we run this, you're going to see it's changing fairly quickly. This is how we would see it in real time as it's running. So the inferences that it's making are very quick. You can see often less than a half a second. This is set up so we can visually see that it's working and it's running, and we can see some of the results as it's going. All right, what other applications do we have, and how do we use that in ArcGIS Pro? Here's an example of a couple of the images. We have the red box for the actual pole and then the blue polygon for the shadow. After we started detecting these, we figured out it was a lot easier to detect a long shadow than a very tiny pole with imagery. So it helped us. We were trying to detect both. And by using the shadow, we can also detect different types of poles. So for example, a light pole, we cannot construct fiber design on that, but a utility pole we can. And they have different shadows where you can see utility pole kind of looks like a straight up and down or kind of like a T, and then a utility pole kind of looks more like a 7 or an L. Here's what it looks like in ArcGIS Pro. So we can go to any of our polygons that it creates. We can look at the attribute table and pull up the class name, the confidence level, and after we look at the data, we can determine what confidence score we're most comfortable with in order to implement that into our design. Next, we also take OpenStreetMap road center lines, and we essentially run something similar to a NIR, where we can count the amount of poles along a road stretch. As you can see here on the far right of the attribute table, we have a count of the amount of poles. We have the length of the specific road segment, and also how many poles per kilometer were calculated. Using these metrics, we can then establish a construction type, whether it's going to be buried or aerial for our design. Here's an example of how it would look. We have a lot of poles along this east to west stretch here. You can see we've labeled it green to show that it's possible aerial. And since the red road going north and south doesn't meet the threshold of poles along its stretch, we've labeled that as buried. It's a quick and easy way for us to do very quick analysis and be able to check from there. Next, we also look at houses. Normally, when we're doing a design, we'll get address points from the state or county or whatever, and if you've ever worked with address data sets, they're not always perfect and they're geocoded. So we want to make sure whatever we are actually building to is going to be a revenue generating customer for a client. So we use this to quickly check for house structures, whether it's in the middle of a field, in the middle of a lake, on a silo, on a barn. So I will also let this run. Again, this is going to be running in real time as we would see it. You can see we have different colors for our polygons based on what it's detecting, as well as the attribute table down below. All of this goes into ArcGIS Pro after it's done running. All right. From there, this is how we usually get the data. On the right, you can kind of see that we have some just normal circles on some address points. You can see one's in the middle of a field, a couple are on some trees. On the left-hand side is what we've actually detected. What we do is we created a script using AI and ChatGPT to help us take these address points and then create a polygon around the points so we can then send those as images to our AI tool to help us detect. So we're limiting the amount of requests we're sending to our API instead of just sending the whole area in general. Here's what that looks like after it's done running. We have the green box, which is what was sent to the AI tool, and then the red polygons for what was detected inside. Very similar, here's what it looks like with the attribute table and the different colors for the different structures that were found. In the bottom right, you can see we identified a trailer in green, all of the houses in red, and then there is a barn or garage or a shed near the bottom. We also have a tool that will look at 3D video and detect poles. This is it detecting poles in real time and updating frame by frame for the confidence level. This is a 360 video that we went out and took in a rural area. A lot of these areas don't have Google Street View, so it's really hard to see the condition of in the field and what it looks like. This is something we're currently working on, and we're hoping to be able to plot these poles and other utilities in GIS Pro so we don't have to go out and manually collect all of this information. We can use AI to help us collect that quicker. All right, so how does this all go into the design, and what else do we look for? We also pull in soil data from the USGS. As you can see, the polygons are very sporadic. We've pulled in the attribute table, and we look at rock size, what type of rock, how much is there, the volume of it, all sorts of things. We collaborated with our environmental team to come up with a matrix on what type of buckets these would fall into. So looking at those and analyzing them, we came up with 5 different buckets. I changed the symbology for easier viewing. We have green areas that there are no increased rock whenever we're constructing. We have yellow and orange for a little more moderate to low risk. And also red where there is a lot of rock present. That's going to greatly offset the costs of doing construction because you need more specialized equipment. It's going to take longer, and it's much more difficult. After that, we'll take OpenStreetMap road center lines, similar to what we did for the poles, and we'll overlay those polygons with the different buckets for the risk level. That's where we get the top right image. And after you take away the polygons and zoom out, you now have the rock and cobble risks associated with the roads that we would potentially use for our design. All right, I got a bunch of videos on a lot of the scripts and tools that we put together. Here is an example of an area just north of here, Hanging Rock State Park. I wanted to show you what the soil data looked like. So as you can see, it's not a great place to construct underground fiber. I went ahead and added a little bit of transparency to it. I used the ArcGIS Pro swipe tool so you can see the difference between just a normal imagery and then our soil data. All right, next, I have some roads that I pulled in. I've attributed based on different costs. We'll go into that more in the next couple slides as well. But as you can see here, you mainly just see a bunch of blue lines. These are ones where we have some light blue polygons for poles we've detected. And I'm going to use the same thing. I'm going to do the swipe tool to take away those polygons so you can see the lines based on the costing of the actual soil. So we're going to see a lot of short segments because of the polygons and how the soil looks in the area. The next thing we will look at will be the actual poles and shadows that we detected along this pathway here. I'll zoom in so we can take a look at a couple of them. As you can tell, we got the poles, we have the shadows. Show you a couple more along the path. Doing these manually would take a long time for our potential build area. So if I zoom out, you'll see the full extent of the example that we did here. There's a lot of poles everywhere. So something this size would roughly take our tool about an hour or so to detect all of the potential poles. All right, next, I pulled in some example addresses. All of the green points are areas we would want to build to. We've already done the analysis on the rock, the poles, the houses, all of that's taken care of. I went ahead and put some example pricing in there. So we have $5 per foot for aerial. We have 10 for normal buried. We have 20 for more rock in the area, and then 50 for the worst areas. We created some tools that we pull in as an add-in. Up top, you can see we have a bunch of little buttons. The first one I'm going to showcase is our FDH, which is a fiber distribution hut. Whenever you want to design, there are different types of fibers. So you'll have a large fiber that starts at what they call a central office, where the internet connection originates from. And then from there, we'll use an FDH or a splice to take smaller cables to go to each individual house to get you connected up and get you some internet. We have parameters over here on the right. This is just so we can decide what area is going to run, what layers we're using. We also have the ability to use our cost per foot that we've decided, or we can go just straight based on distance, whatever is most effective. We can also change the groupings for each of these. We have to have logical groupings and where we're going to place our splice locations. So I'm going to go ahead and play the video. You can see I have 2 areas selected. In this area, there's roughly 3,300 addresses. If I was going to do these groupings manually, it would probably take me a couple days, if not a week. However, with the help of automation, I won't reveal it, but we'll show how long it takes. In this example, I used 25,000 feet for our groupings. We also have the tool set up so it's going to output messages so we can see exactly what is happening, what step it's on. In the messages, you can see that it is analyzing 36,628 possible locations to place these splices. And it's done. It took about 19 seconds to do all of these groupings. It would take me more than 19 seconds to do one of them by myself. So this looks very overwhelming. We have a lot of visual layers that we can use to help make logical decisions based on what the program decided to run for the code. I went ahead and changed the symbology a little bit to make it a little bit easier to see. We have a lot of visual layers that just help us see what's happening. We have layers that are created to help us find problem areas, issues that would arise once we run future steps. So for example here, I'll zoom into this area with some red circles. These are areas where a house is being fed from 2 different groupings. We don't want to build to it twice, we only want to build to it once. So we can identify those and change our grouping areas to fix those. We can also see where each of these houses originate from. So in this example, you can see it was originally designed from the one up north. We also have these warning signs that show us addresses that are not snapped to a road that is part of the entire network that we are considering. To fix that, all we have to do is just extend our lines just using modify features. All right, so after taking that, it took me about 30 minutes to make sure everything looked good, all the groupings make sense. Next, we have another tool that will route from the central office to all of our splices, then to each address. Specifically for this example, we're using the most cost-effective method based on the values we input, and it's not going to necessarily pick the shortest. The same thing, where it's going to output some layers on the left for us to visually see what's being added. We have messages that are updating in real time as it's creating all of these routes for us. Again, we have some layers that we can look at, such as if a design goes into another project area, so we don't want to have overlapping cables, we'd prefer to have just one. This tool took 26 seconds to run. If I were to go into Arc and manually draw all of these lines, again, it would take me a very long time. So we're able to save a lot of time and spend more time figuring out what the best path would be based on what the algorithm decided based on the costing. All right, the next tool we have, we call it our IRR, or internal rate of return tool. A lot of times, our client has specific metrics they want to hit, how many clients they want to hit, and how much an overall build can cost. So we're able to use our tool to help us trim out projects to be the most cost-effective, to have the most addresses, to make sure we're getting as much people coverage as we can. This is just going to show that we have a bunch of attributes inside of our fiber. We have the cost, we have the construction type, the aerial, and the buried. And then we also have the type of fiber, whether it's those bigger feeder cables or the smaller distribution cables. Here is the IRR tool. Again, we have parameters on the right that we can change how much of a grant is going to be supported, whether there's 0% up to 100%. We also have different internal rate of return target percentages. So here is a video where we show what was actually trimmed from the project. This one took about 5 to 10 minutes to run. Everything that was kept are going to be those green addresses and the green lines. Everything that was cut is going to be the red along with the black circles. Doing all of this manually would also take a very long time to be able to calculate how much each section is going to cost for our client. The last step we have is we have done a lot of bead designs for different states. Each state is a little different. They went ahead and started grouping addresses together in things they call project area units. For this example, there are hexes that are put together. Some of them are multi-parts. And they've said, if you're going to design to anything in this project area unit, you have to design to all of it or design to none of it. So that threw a wrench in our internal rate of return program. So we decided to make a second one that's also going to trim based on these project area units. So I'll zoom into an area here where you can see along this road, we have the black addresses that were trimmed because they're part of the northern area. But along that same route, we have the green addresses that stayed. We have a couple Excels that output to show us exactly what is trimmed, the overall cost of what was trimmed, and the specific roads and addresses that were trimmed so we can go and verify what's happening, as well as a couple more that show us what started and what it ended with and some overall metrics that we can show the client so they can also verify and check what's going on. All right, we went over how we use a bunch of advanced analytics and AI in our overall planning, strategy, and design. We talked about how we created those AI tools and the models, and how we implement that with our overall design. Does anybody have any questions? Yes?
I've got 2 questions.
Sure.
So the first question, for the imagery, like building recognition, do you consider using like a leaf-off imagery to be able to find those buildings that are underneath, you know, it's an address point that's underneath trees most of the time, but then you have leaf-off imagery to kind of train it for finding those?
We have not. There is some manual checks that we do. That is something that we can definitely consider that we can build into our tool. But currently we don't. We'll have areas that are not detected, and if we'll verify them, double check what was found, and then use that as future training data to where we update our models. But that is a great idea that we haven't done yet.
And then my second question is, do you have any capability built into your like to set spaces for, hey, we're gonna have loops and splices and handholds like at these points, or is that just you still add that in manually after for your typical breakpoints?
Yeah, so we could. We currently don't have it. What we're specifically using it for is very high-level grant planning, to where they don't really consider that. They take a lot of statistics like, hey, every X amount of feet, we're going to add a handhold. So we don't have it specifically, but it's something we could definitely work in to our program. Thank you. Yes?
Has the AI tool gotten better as you trained it?
Yes. The more training data we add to it, you have to rerun it again for it to relearn all of the stuff, and every area is a little different. Sometimes the grass is different colors, sometimes the trees are a little different, so each area kind of has its own AI model that we run to help us detect, but yeah, for the most part, it gets better as we continue to train it.
For those training data sets, like you have a rough estimate on like how many features you guys have found success with to have a good, solid training set?
Yeah, it varies based on how much we're going to do. Sometimes we'll do entire states, sometimes very little, but pretty much as much as you can. we'll usually spend a couple of days just gathering images and putting labels on it. I'm not exactly sure how many that is because it varies so much, but yeah, I mean, the more you add to it, the better it's going to be. For example, when we first started detecting it, we found a lot of fences that have that T shape when you throw the shadow. So being able to put the false positive in there in the training data and then label those as, hey, we don't want to find this, it helps a lot. So it kind of varies. Yes?
For the AI pool imagery identification, what sort of framework are you looking to implement to transition those into R?
Great question. I didn't specifically design the program, so I'm not 100% sure, but I know we use a lot of open source libraries, and specifically we use the YOLO V8 model to help us detect it. I know we have some code set up on the back end that will analyze that and then place that. If you're familiar with ArcPy, there's a lot of search cursors and update cursors that will, and insert cursors that do that for us. So I'm not 100% sure, but that's a great question. I can get back to you on that one. All right, thank you so much.